we talking about last time? Yep, changes in state functions. What was the purpose? Like, why do we care about doing that? What were we trying to work our way towards? Or did I actually even say what we were working towards or why we were doing it?
Let's say U equals the integral CV dt.
Yeah, so we're trying to look at heat capacities. So heat capacities are nice because all you need to do is know the change in temperature. Bam, you know the heat exchange, and then a lot of times you can tell what is the change in internal energy or enthalpy. So we're going to talk about heat capacities. Before we do that, we derived some changes in properties, and we set specific parameters that we wanted to look at, specific variables, right? What was it for U that I said we were going to keep track of?
Temperature and volume.
Yep, U was a function of temperature and volume. Would it have to only be these two variables? No, we could have swapped in pressure, but we're going to keep it this way because it makes the math easier later on. Trust me on that one for now. And then what did we say this infinitesimal change was? Partial of what?
U.
Yep, over.
Partial T. Over B constant.
Yep, times.
dt.
Yep, and then what was the other portion?
Partial U. And partial B. Over T.
D what?
Shouldn't that be partial B?
Yeah, should be. Woo! Got excited.
dB.
D. There we go. Okay, and then we had another one for enthalpy, right? And what did we say enthalpy was a function of?
Pressure and temperature.
B and T. Of course, we could have thrown in volume. We don't want to because it makes life hard. What would this differential be equal to? Partial of
H.
G over what?
Partial B.
Sure. Keeping what constant? D what?
H.
Yep. Plus partial, oops, off, why did I write with U? H. Differentiating with what?
T.
Yep. Keeping P constant times what? Okay, we're going to use these again in a minute. So just as a reminder, those are there. Okay, so let's talk about heat capacities. Heat capacity is defined as the change in heat over a change in temperature. So really when we're talking about this thing, we're talking about the change in heat or the heat exchange with respect to temperature. Because are heat and temperature the same thing? No, they are not. They are different. Generally, when you consider heat capacities, they come in two flavors or two types. Given the other experimental conditions we've considered so far, we're going to hold two things constant. What two things do you think we're going to hold constant? What was that?
Pressure.
Yep, constant pressure. And constant what? Yep. Constant volume. Okay. Which one of these do you think will be more useful to us as chemists? In terms of these experimental conditions?
Constant pressure.
Yeah, constant pressure. However, you can actually tease out relationships between these two. And let's say you only know one of these values, you can figure out the other. And different relationships associated with this constantly fall out of the mathematics. It's weird. It's like, why does pi show up all the time? with these, it has to deal with something in statistical mechanics where you consider little particles, and these numbers just keep falling out over and over again. It's kind of weird. It's like the golden ratio. Have you guys ever talked about the golden ratio? Yeah? Is that the one where it's like you measure your foot and you measure your arm and they're always in a certain ratio or something? Or what is the golden ratio? Anybody know?
I thought it was like the one that plants follow, like flowers and stuff.
Yeah. I think there's that one. I thought it was like something with like the size of your arm and your foot. Like if you measure your forearm, you get your foot right every single time. Really weird. I have to have Dr. Hill or Dr. Yule talk about it because they like that crazy stuff. Okay, so let's tackle constant volume heat capacity first. And heat capacity generally is C. What symbol do you think we're going to give this? C sub what? Yep. CV. Okay. Let's first consider one of our differentials. Let's look at du TV. We've already set this up. QT T plus Q partial of V. Yeah. Do we have any other way to express du? What was that?
Delta U.
We can get a delta U if we integrate. I don't want that. Any other tricks or equations from the first law that we could utilize? Delta U is equal to what? Yeah, that's integrating, that's what I like. Okay, Q plus W. So what would du be equal to? Yep. Q plus E. Okay. What we're going to do now is assume we only have pressure volume work. Oops, not dq, dw. What does dw become if we only consider pressure volume work? So do you guys know what I mean by pressure volume work or not really? Yeah. What does pressure volume work? Pressure volume work. What's doing the work besides my hand right now? When I let go of this, what's doing the work?
Gas.
Gas. How'd you find work associated with the gas?
Negative P external
Yeah.
times volume.
Yep. We're going to be a little more general. We're going to leave it as the pressure of the gas, dV. So let's sub that in here. So we get partial to U, partial to T, constant V, T, plus that portion. Okay. What do we care about finding here? We want to try and find heat capacity, right? So we're trying to find something like this. What we really care about is the thing on top, that dq. Do we have a dq in our equation? Okay. Yep, got one right here. Let's try to isolate this. What would you do to isolate this?
Add PEV to
Yeah. Okay. Can we combine any like terms? Or simplify this in any way? How do you see to simplify this?
a lot of PEV from the last one.
Yeah, we're gonna pull out a dv here. Oops. Partial of u, partial of t plus, what do we have? Partial of u, partial of v, holding t constant, minus, oh, plus b, sorry. This is a useful expression. It's gonna come back to us at some point, see it again later. Okay. We've kind of hit a wall here though. What would you suggest to do now to get to a constant volume heat capacity? Or any assumptions we could make to simplify this equation? dV is 0. Okay, we want dV to be 0. We want this thing to be 0. But how can we make it happen? What do we need for experimental conditions? Yeah, constant volume. So if we have a constant volume, yeah, that's gonna shoot way down. And it's gonna disappear. So we're left over with this. Heat capacity is defined as what? Oh, we should change one more thing in here. What other thing should we change in this equation, given we have constant volume?
Dr. Simpson, is that first term supposed to be T holding D constant?
Yeah, it should be. Jeez, terrible. Try that again. Beep. Okay, I did it right over there. I just translated. Where else do we need a sub V though? Yeah, this DQ, we just want to specify that. Okay. So now, what did we define heat capacity as?
DQ,
Okay, what can we do here?
Divide dt.
Yeah, divide by dt. Mathematicians don't like that, but we're going to do it anyways. Divide by dt. And when we do that, we get dq sub v, t is equal to change in internal energy, change in temperature, and constant volume. That's where we have our constant volume, heat capacity. Cool. Okay, let's show the utility of this though. Like how does this actually help us out? So heat capacities, they tend to be functions of temperature. You can find them, but also a lot of times they're assumed to be constant over a specific pressure and temperature range. So literally all you have to do is look up constants for whatever compound you're considering and plug them in, and you can get a heat exchange that way. So, first question. What if we want to know total heat exchange at constant volume? So we want Q sub V. If we look at the integral of dQ sub V, that's tough to do, right? Where we're looking at some initial temperature, some final temperature. But now we have something that can sub in here, which we determined right over on this side, right? What is dQ going to be equal to?
The partial of the other partial two,
Mm-hmm.
you're gonna be constant.
Okay. And what's this thing that we showed a little bit ago? Yeah, that's CV. So in reality, okay, the beauty of this is most of the time this is just a constant. So what could we do to this? Yeah, so I'm gonna put a star here. Most of the time. There are times where that is not true. Easiest integral of your life. What's that integral? Yeah, it's delta t, right? Okay, when you have to measure something in the lab, and we have 3 different parameters, we got pressure, volume, and temperature. Which one would you favor to measure? Which one's the easiest for you? Which one has the least amount of error? Temperature. Temperature's great. Pop in a thermometer, a thermocouple, bam, you get your answer, you move on with your life. That's what you can do here. It's nice. Now, another question. I'm not telling you the whole story with this though. So like, okay, we get the heat exchange, big whoop. But how does that relate to other state functions? So question. How do Q and delta U relate under constant volume? So do you guys remember how they relate to one another? Yeah, they're equal to each other. So when you do this, you get the change in internal energy, which is awesome. It's something hard to find out. Now all we have to do, look up a constant in a table, plug in dt, bingo bango, we got what we need. We can move on with our lives. But under what conditions is that for?
Constant volume.
Constant volume. How useful is constant volume, really? Like I said, you've done probably, well, 2 people in the room who've done 1 experiment, everybody else probably never, right? Let's look at constant pressure heat capacity.